In this video, we're going to look at the idea of pH, and pH incidentally has a small p and a large h, and it might stand for power of hydrogen. No one's really quite sure. It's lost in the darkness of time. So pH is defined as being the negative of the base 10 logarithm of the hydrogen of the hydronium ion concentration. And we can actually flip that on its head. We can go ahead and we can say the log of H plus is minus pH, and we can anti-log that to get just the concentration of H plus by itself, and that is 10 to the minus pH. And so that's going to be very useful for us. For instance, if we've got an H plus concentration that, like in the last video, was say 1.0 times 10 to the minus 3, we can calculate the pH by just taking the negative base 10 logarithm of 1 times 10 to the minus 3. We just throw away the units, and that gives us 3. Our calculator will say 3, but actually we've got to be a little bit careful here. The number of significant figures, which in a scientifically notation written number, if that's such a phrase, is just the number of sig figs of the thing before the times 10 to the power. So in this case, we've got 2 significant figures, turns into the number of decimal places. So these are exactly the same. So if we've got 2 significant figures, we're supposed to write this to 2 decimal places, so 3.00. Practically what we'll find is that it's very hard to measure better than 2 decimal places. So it's really hard to measure more precisely than plus or minus 0.01. And so in the lab, you can get pH meters that will read at 1 more digit, but it's kind of a tough one to measure. So practically speaking, it's very unusual to report a pH to more than 2 decimal places. We'll probably fudge it all the way through this chapter and make sure they always come out to be 2 decimal places. But sometimes if we have 3 or 4, we will be tempted not to write those extra digits on anyway. So let's go ahead and look at another H plus concentration and calculate the pH. So here's one for you to try. So we remember in a neutral solution, the concentration of H plus at room temperature is 1 times 10 to the minus 7. Can you turn this into a pH? So go ahead and stop the video and calculate a pH to the correct number of significant or decimal places. All right, so if you're back, what we have to do is just take the negative base 10 logarithm of 1 times 10 to the minus 7, and our calculator will just say 7. Okay, remember, if you get minus 7, you need to flip the sign out front, right? So there's a little minus button on a lot of calculators written in parentheses. It looks something like this. So if you press that before the log, that will often do the trick. So the number of decimal places is the number of significant figures in the original number. So 1.0 has 2 sig figs, so our final pH should be 7.00. So notice that is a neutral scale. In fact, if we go ahead and we draw the pH scale out, we can write 7 here in the center, and we can say that this is our definition of neutral at 25 degrees Celsius. If you are below that number, so if you're below 7, then you are acidic, again, just at room temperature. And if you are above 7, then you are basic, again, just at room temperature. And just a quick figure from our textbook here. And so this is the pH scale here. So we see increasing pH is increasingly more basic. In fact, I always think the scale is backwards because the lower the pH is, the more acidic it is. But because pH is defined as a negative base 10 logarithm, what that means is every time the pH changes by 1 unit, the concentration of H plus changes by a factor of 10. In fact, every time we increase the pH by 1 unit, the H plus concentration decreases by 10. And every time we decrease the pH by 1 unit, the H plus concentration increases by 10. So it's a deceptive scale. You might think going from 7 to 4 is no big deal. It's 3 units. But in terms of concentration, it's a factor of 10, another 10, and another 10. So there is 1,000 times more hydrogen ions at a pH of 4 than a pH of 7. Makes a huge difference.